Welcome to BTEC Revision. In today's lesson, we're looking at magnetic flux density. By the end, we should be able to calculate the magnetic flux density, magnetic flux, and area. How can we represent the strength of a magnet? Below, we have a picture of a magnet. We have the north and south pole of the magnet, and lines that are coming out from the north and going into the south poles. These lines are representing a magnetic field, and a field is a region of space where an object experiences a force. In this case, we are looking at magnetic fields, so a magnet would experience a force, or a magnetic material. For example, iron, cobalt, or nickel. The magnetic field lines have a direction, and they go from north to south, as you can see in the picture. And the closer these lines are, the stronger the magnetic field is. For example, if you look at the ends of the poles, the north and the south, all the lines are closest at those regions. Therefore, the magnet is the strongest at those points. Next, we can look at magnetic flux, which is a measure of the quantity of magnetic field lines passing through a surface. In this picture below, we have these lines representing the magnetic field, and they're going through a object which has a surface area A. And the amount of these magnetic field lines going through this area is known as the magnetic flux. And the short form symbol for this is phi. Next, we can look at magnetic flux density, which is a measure of the strength of the magnetic field and can be calculated using this equation. Magnetic flux density equals magnetic flux divided by area. And the short form is B equals phi divided by A, where A stands for area and is measured in meters squared. Phi stands for magnetic flux and is measured in a unit called Webers. That's WB for short, and Webers is spelled as WEBERS. And B is short for magnetic flux density, which is measured in a unit called Tesla, T for short, and the spelling is TESLA. It is important not to confuse magnetic flux density with magnetic flux. Magnetic flux density is the ratio of magnetic flux with the area. So it is measuring how much magnetic flux we have per unit area. Let's look at an example. A magnetic field has a magnetic flux density of 20 millitesla. If this field passes through a surface with a cross-sectional area of 0.1 meters squared, calculate the magnetic flux. We can start by writing down our equation, B equals phi divided by A. And we know phi, which is 20 millitesla, so that's 20 times 10 to the power of minus 3, divided by an area, 0.1. And that would give us a value of 20 times 10 to the power of minus 2. And the unit would be Tesla. Now pause the video here and attempt this exam question. We can start by writing down our equation. B equals phi over A. We know phi is 200 milli, which is times 10 to the power of minus 3, divided by the area. But we don't have the area, we have 3 millimeters. Looking at the solenoid, which is a coiled wire, looking at the side view, it would look something like this. So a circle. And from the center of the solenoid to the edge is a distance of 3 millimeters. So that's going to be the radius. And the radius is 3 times 10 to the power of minus 3 because it's millimeters. And we can work out the area. Area equals pi r squared. Therefore, we can times pi with 3 times 10 to the power of minus 3, and that needs to be squared. And this gives us a value of 2.827 times 10 to the power of minus 5. And now we can plug that into our first equation, 2.827 times 10 to the power minus 5, and 200 times 10 to the power minus 3 divided by our answer, gives us a value of 7074. The unit is Tesla. And that's the end of the lesson. If you'd like to boost your grades, visit us at btechrevision.com, where there's lots of quiz questions and more resources. See you next lesson.